Okay, welcome back. We're going to look at an example of two examples of monotone sequences. So here's a preview of what we're going to see. To remind us of these properties, do recall how we define an increasing sequence. For every term, a n plus 1, it has to be greater than the one before it, a sub n. A less restrictive property would be a non-decreasing sequence. So each a sub n plus 1 would be greater than or maybe equal to a sub n. So the subsequent terms are larger or equal to the previous terms, the ones before it. Okay. So these two properties are similar to how we used to describe continuous functions. If we could show that f prime of x was positive for all x on an interval, then the function itself was increasing on that interval. Or a little less restrictive if we showed that f prime of x was greater than or maybe equal to 0 on an interval, then the function f was non-decreasing, because it could be constant or have a turning point in some places. Okay. The vocabulary words decreasing, non-increasing are defined similarly, and we would say that a sequence is monotonic, mono meaning one, having one property, monotonic, if it's either non-increasing or non-decreasing for all n. And two quick examples that wouldn't take much proof. Fibonacci, you could see, is non-decreasing. It's constant and then it's increasing, so for overall it's non-decreasing. The geometric sequence, where the common ratio is 1/2, the terms always get smaller as you go, so that would be a decreasing sequence. You could say it's non-increasing. That'd be less restricted, but it is actually decreasing. Okay. So back to the example we saw at the intro. We're going to look at two examples and use two different techniques to show monotonicity. So we have the sequence where each term is 2 minus 1 over n squared. We want to show that it's monotonic. Just to give ourselves an idea of which way it should go, let's let n equal 1. Then let's n equal 2. Oh dear, what's 2 minus 1/4? 7/4. And when n equals 3, 1/9, would that be 17/9? Okay, so it actually looks like it's what? Increasing, huh? Because we go up from 1 to 1 3/4, and then we're almost up to 2. We're up to 1 and what? 8/9. So we think it's going to be increasing. Now, because of this algebraic form of each term, we can take a derivative. Let's just think in terms of x for now, because it's kind of hard to write the derivative in terms of n. So if we take the derivative of the function 2 minus 1 over x squared, we might rewrite that so that we can use the power rule, 2 minus x to the negative 2. And the derivative of the constant, well, that's just 0. And the derivative of negative x to the negative 2 becomes positive 2x to the negative 3, or 2 over x cubed. Okay, so it may not be clear if this function is always positive or always negative. But sequences, we know that we're going to let n go off to infinity, and n is going to be greater than 1, so n is positive. So we can assume that x is positive, and that would imply this ratio is positive. So if the derivative of this function is positive, this continuous function is an increasing function, and that means our sequence is an increasing sequence. Okay. So that was example 1. Let's take a moment and look at Another example that needs a little bit different approach, and looking at my notes, that sequence is going to be 1 plus 1 over n factorial. And so the having this factorial term rules out using derivatives, at least directly. Okay. Is the sequence monotonic? Okay, well, let's just take a look at a few terms. 1 plus 1 over 1 factorial, that's just going to be 2. That's 1 plus 1. And then 1 plus 1 over 2 factorial is going to be 1 plus a half. Now when n is 3, we're going to end up with a 6 here. And when n is 4, we're going to end up with a 24 in the denominator. And it looks like, well, it looks like the terms are approaching 1, but what we're looking at is that the terms seem to be decreasing towards 1. So we'd like to show that this is decreasing. Can we show that subsequent terms are smaller than the preceding terms? Okay. If so, then a sub n is decreasing, and therefore monotone, or monotonic, I think is what the publisher is currently saying. Okay. Well, again, we're dealing with sequences, and let's assume n is greater than 1. So, or at least we can suppose that n is positive, and that would imply that n plus 1 is greater than 1. Adding 1 to both sides, we keep this relation. And then if we multiply both sides by a positive factor, the relation stays true. And so continuing with the logic, we could rewrite this product on the left-hand side, n plus 1 times n minus 1. This product can be wrapped up and rewritten as a simpler factorial. So it's very straightforward to show this relation. Okay, but our sequence is written with reciprocal terms with the factorial, and if we take the reciprocal of each side of this inequality, then that will flip the inequality, and we're starting to look like the terms of our sequence. Now all we have to do is add 1 to both sides, and we've shown that a sub n plus 1 is less than a sub n from the original sequence. And our sequence is decreasing, therefore monotone. Just like my voice was then. Ooh. Okay. Thank you.